All right, so this is a static equilibrium example. So let's take a look at this. So we have an 80 kilogram construction worker who sits down 2 meters from the end of a 1450 kilogram steel beam to eat his lunch. The cable supporting the beam is rated at 15,000 newtons. Question is, should the worker be worried? So the reason why the worker might need to be worried is because the structure here was not designed to have a person sitting on it. So it is possible that with the added weight of the person, we might exceed the 15,000 Newton limit for the cable, and the cable might break. So what we're going to have to do is calculate how much is the tension in the cable when the worker is sitting where he's sitting, and see if that tension is less or more than the 15,000 Newton limit. So that's the plan. All right, to do that, we're going to first define what is the system that we're dealing with. So we're going to be looking at the beam, and we're going to assume that the beam doesn't move, which means that the beam doesn't move to the right, it doesn't move up or down, and the beam also doesn't rotate. Notice that the beam has a hinge on the left-hand side, and so rotationally speaking, we need to have that beam in equilibrium, not rotating. So the sum of the torques on the beam must be 0, and linearly or translationally moving, we must guarantee that the forces cancel in the vertical direction and they cancel also in the horizontal direction. So the system that we're dealing with, the beam, has forces. So whenever we want to figure out what are the forces acting on a system, we need to look at what is touching the system, the object of interest. So in this case, for the beam, we have the worker sitting on top of the beam. So the worker is going to be exerting a force downwards on the beam, and that force is going to have a magnitude equal to the weight of the worker. So we're going to call that MP for the mass of the person times G, and that's one of the forces. This force is acting 2 meters away from the right end of the beam. Okay, so that's important because we're going to have to calculate torque, the torque of this force. So we need to know where the force is. Now the torques are going to be calculated with respect to the axis of rotation. In this case, the best place to set up as our axis of rotation is going to be the location of the hinge. So we need the force of the weight of the person, we need that force, and we need to have the distance from that force to the axis of rotation. So we're going to use that 4 meters as the moment arm for that force. Another force acting on the beam is the tension of the cable. Tension always acts along the direction of the cable, along the cable. So this tension force, the cable is attached to the right end of the beam, so the tension force of the cable is acting at that location. The weight of the beam is one of the forces that we need to consider. They gave us the mass of the beam, which is 1450 kilograms. So clearly the beam has some weight. And remember that for a uniform beam or rod, the center of mass is going to be in the middle. And at the location of the center mass, we're going to put or set up the weight of the beam. So the force of gravity acting on the beam can be thought of as acting in the middle of the beam. Again, this is important because the distance between the weight of the beam and the axis of rotation is going to be important to calculate the torque, and that distance then is going to be 3 meters. So we assume all the weight of the beam is concentrated in the middle, and that force we're calling it MB times G, MB for the mass of the beam, 3 meters away from the axis of rotation. Now another force that is acting on the beam is the force of the hinge, right? The hinge it's applying a force to the beam, it's touching the beam, so therefore you can assume that there is a force there, and so there's a force there. Now the good thing about the having chosen the axis of rotation at that location, at the place where the hinge is that the force of the hinge is not going to have any torque. Okay, so that's going to be an important consideration when we write the equation for the sum of the torques. So let's see, we have the information given in the statement of the problem. It allows us to calculate these forces that I'm putting a check mark next to it. We have the mass of the person, we have the mass of the beam, G is 9.8. So we're gonna need to use that information and the distances to calculate what is the tension in that cable. One thing that we don't know at this point is the force of the hinge, right? Or I call that FW for force of the wall. So we don't know how much is that force. We don't know in what direction it is. So at this point, we're just kind of looking at what information we have, what are we looking for, what are the unknowns, what are the knowns. So the first equation that we can take a look at is in static equilibrium. Remember that because the object is not moving in the x direction, the acceleration in the x direction is 0. Therefore, the sum of the forces in the x direction is also 0. So this is one of the equations that we can always use in static equilibrium problems. So we spell out what forces have x components. So you see that the excuse me, the weight of the person and the weight of the beam are not horizontal forces, but the tension does have an x component, and the force of the wall possibly can also have an x component. So the equation that we're getting then is the tension x component is t cosine 30 degrees. The angle between the cable and the beam is 30, but it is pointing to the left, so don't forget about the minus sign. Minus t times the cosine of 30 degrees plus whatever x component the force of the wall has. And those are the only two forces with x components. They add up to 0. So that tells us that the x component of the force of the wall is positive and is equal to the magnitude of the tension multiplied by the cosine of 30 degrees. So notice that we know at least something here about the direction in which the force of the wall is acting. We know that the force of the wall has a positive x component, so it must be pointing to the right, which makes perfect sense because notice that the tension in the x direction is trying to make the beam dig into the wall. So the wall is going to be pushing back on the beam in the opposite direction, meaning in the positive x direction. So another equation that we can write is, of course, exploit the fact that the beam is not accelerating vertically, so the sum of the forces in the y direction is 0. All right, so the sum of the forces in the y direction must be 0 because there's no acceleration. And what are the forces in the y direction? So the tension has a vertical component. The vertical component of the tension is going to be the component, vertical component. So t sine of 30 degrees gives you the vertical component. We have the force of the wall, which is going to have some kind of y component. We don't know how much it is, so we just leave it for now like that. And vertically down, we have the two weights, the weight of the person and the weight of the beam. So minus mpg minus mbg, and all of those vertical components of the forces add up to 0. So far we have two components. We have the equation for the x components. We have the equation for the y components, two equations. So notice that these two equations have the tension there. So in principle, we could find tension there. However, we can't because the unknowns force of the wall in the x component and the force of the wall in the y component prevents us from being able to solve for the tension. So at this point, our last shot is to use the equation, the third equation for static equilibrium, which is the sum of the torques about any point should be equal to 0. So at this point, you always have to choose what is the pivot for your calculation. So clearly, what we're going to use is the hinge as the pivot point. So if we choose the hinge, then the torque of the force of the wall would be 0. We will not have to calculate that torque, and then we'll have an equation that does not involve the unknown force of the wall. So that seems promising. So the equation then says that the torque of the tension plus the torque of the weight of the person plus the torque of the weight of the beam should be equal to 0. So what is the torque of the tension? So the tension is a force that is acting at 30 degrees from the beam. The force is attached to a point 6 meters away from the hinge. So we're going to do the value of the tension, T, multiplied by the sine of 30 degrees. That will give us the component of the tension perpendicular to the beam. So that is one way to calculate torque, which is to find the component of the force perpendicular to the position vector. So we do that with T sine 30, and then we're going to multiply by 6 meters because that's the distance at which the tension is applied. So that's the torque of the tension. And notice the positive sign because the tension by itself would make the beam rotate in the counterclockwise direction. Counterclockwise direction is what we call the positive direction for rotation. So the torque of the tension is plus T for tension times the sine of 30 degrees times 6 meters. The next one that we're calculating there is the torque of the weight of the person. So the force that the person puts on the beam is equal to his weight, and that is MP times G. That's the weight of the person. The force is applied 4 meters away from the hinge. So we multiply by 4, which is the moment arm. And we're putting a minus sign there because by itself, the weight of the person would make the beam rotate in the clockwise direction, and that is the negative direction for rotation. All right, we have one more torque to calculate. That's the torque of the weight of the beam. So the weight of the beam is the vector that you see in the middle, the mass of the beam times G, and that is acting 3 meters away from the pivot. So the torque of the weight of the beam then is also clockwise, so minus MB times G times 3 meters. And all of those torques added together should be equal to 0. So that's our equation for the sum of the torques equal to 0. So notice that in this equation, we have everything is known. We have the masses for the person and the beam. We have those. The value of G, which is 9.8. So everything there is known except for the tension. So this is the equation that we've been looking for. This is the equation that will give us the tension acting on the tension in the cable when the person is sitting at that location. So we're going to solve this equation. The first term is T sine of 30 times 6 meters. The sine of 30 degrees is 0.5. So 0.5 times 6 is 3. So I'm writing that as 3 meters times the tension minus the 4 meters, which is the moment arm of the weight of the person. The weight of the person is the mass, 80 kilograms, times gravity, 9.8. And the next term is the mass of the beam, which is 1450 kilograms. We're multiplying by G, 9.8, and we're multiplying by 3 meters. And that adds up, all of that adds up to 0. All right. So plug in the numbers in your calculator and solve for the tension. You get 15,255 newtons is the tension in that cable. So clearly we are 255 newtons above the maximum tension that the cable can stand, which tells us that the answer to the question in the problem is that yes, the worker should be worried because that cable will not be able to stand that tension. Now, the number that you see there, that I just show you, this one, is the calculation for the tension in the cable when the person is not there. So if we put 0 for the mass of the person, we find that the tension in the cable, if the person wasn't there, is 14,210 newtons. So the reason why I'm looking at this number is because when an engineer designs a structure, such as the one that we have here, and makes the calculation for the different tensions in the different elements of the system, well, in this case, the engineer who found that the tension in the cable will be 14,210 newtons, well, apparently this would be the same person that would recommend to put a cable with a maximum tension of 15,000 newtons, which, as you can see, it's a pretty dumb idea, because the cable has a maximum tension that is so close to the actual operational tension of the cable that it does not allow for any margin of error. If a bunch of birds were to nest on top of that beam, if the worker constructing this structure decides to take a break on top of the beam, all of these things are potentially going to make that cable break, because the cable is so close, the maximum tension of the cable is so close to the operational tension of this cable. So this is not a way that you design structures to be safe. So in real life, whenever these calculations are done, the engineer will have to multiply things by a safety factor, depending on how critical that element is for the stability of the structure. The calculation will have to, the value, for example, in this case of the tension of 14,210, will have to be multiplied by a safety factor of 2 times 2 or times 3. So times 2, that gives us 28,000 newtons. So you would pick a cable that is rated at 30,000 newtons if you're using a safety factor of 2. So this is how you would do these kind of things in real life. Another interesting calculation is, what is the maximum distance at which the person can be sitting on that beam before the cable breaks? Okay, what's the maximum safe distance to be at from the hinge? So to do that calculation, what you need to do is, in the equation at the bottom, instead of plugging in 4 meters, so instead of using this value 4 meters here, what you want to do is leave it as an x. Replace that 4 meters with an x. And for the tension, we're going to be calculating at what distance the person should be so that the tension reaches 15,000. So that's the maximum. That's as far as the person can go from the hinge. So we're going to plug in for the tension 15,000 newtons. And when you do that calculation and solve for x, you find that the maximum distance is 3 meters. So the worker basically was 1 meter over the maximum distance before the cable breaks. All right, that's it for now.